Okay, very good morning, my dear students. Today we can discuss the probability of error calculation for binary amplitude shift keying technique. So this is the module 4 of chapter 3, and see, after completion of this module, each and every student should be able to derive the expression for probability of error uh, for BASK system. Here already we studied the importance of BASK system and the basic form of BASK signal in the second chapter. So I think you know what is a BASK signal. It is a binary amplitude shift keying signal. How can you define binary ASK? The amplitude of sinusoidal carrier is varied in accordance with or switched in accordance with the input digital signal. Okay, here in the case of binary amplitude shift keying, binary represents that only one bit, because one bit is transmitted per symbol. That means in M array we will group n number of bits per symbol, and so many number of symbols are constructed to form a sequence. So a sequence, information sequence which is transmitted will comprise of various symbols. Okay, and each symbol once again consists of a group of bits. Okay, so a sequence, the entire transmitted sequence consists of a group of symbols, and each symbol once again consists of number of bits. And you should know that in binary ASK only one bit is present in particular symbol. So each symbol consists of only one bit. So our information rate or signaling rate is less in the case of binary transmission techniques over M-array transmission techniques, because in M-array we will group more number of bits, n number of bits per symbol, and so like that more number of symbols are constructed to form a sequence. So the signaling rate is more in the case of M-array transmission techniques, but let us calculate the probability of error for binary ASK. Already we studied everything regarding binary ASK in the chapter 2. Okay, and if you observe binary ASK, in order to calculate the probability of error, you should know the two levels of binary ASK. If that is like known to you, you can easily calculate the probability of error for BASK system. So what are the two levels of binary ASK? Any one of the student, can you tell me, can you explain me the general form or general expression of binary ASK signal? So if you know this, we can easily solve the probability of error. Any one of you, please respond. What is the general expression of binary ASK signal? What is the general form?
Easy cos omega ct, ma'am, for x of t equals to 1.
Okay, very good. And
0 equals to for x of t equals to 0, ma'am.
Okay. What is? Can you write the amplitude of carrier in terms of power dissipated per symbol?
Yes, ma'am. S equals to root over 2 ps.
Okay. So here actually instead of the amplitude of carrier, okay, thank you, Ma. Instead of amplitude of carrier, please represent AC as root 2 ps, because our intention is to calculate the probability of error in terms of output SNR, and output SNR is once again represented in terms of bit energy. So our intention is to represent the probability of error in terms of bit energy, transmitted bit energy. So that's why like our input signal levels, please represent in terms of power dissipated per symbol. Just to replace amplitude of carrier as a root TPS. Okay, and before that, before substitution, already in the last class already we have seen everything. So follow the same procedure. What we did first, we took the general expression for, please observe the first equation. See, the probability of error calculation, the 4 techniques is almost all same. We'll follow the same procedure. So first you consider, we know that the probability of error is half ERFC of x01 of t minus x02 of t divided by 2 root 2 sigma. And this is for the optimum filter. Okay, so every time, because we need the optimum response for optimum evaluation for output SNR, in order to reduce the probability of error, please consider the probability of error expression for optimum filter. Okay, so using optimum filter, we obtain the general expression for probability of error as shown here. So this derivation we calculated in the optimum filter module, that is second module. So, and also we defined what we defined, square of output SNR rho max should be maximized. Okay, what is output SNR in this first expression? X01 of t minus x02 of t is a change in the output signal, divided by sigma is the deviation. So if you take a square for this, that term we defined as max. Okay, so square of output SNR is defined as rho max. Why suffix max? Already I told you so many times that output SNR, square of output SNR should be maximized to reduce the probability of error. Okay, so square of output SNR rho max is considered, and that is maximized. So the expression for that is simply x01 of t minus x02 of t divided by sigma whole square. Here we considered numerator as change in the output signal, that is nothing but the change in the output signal levels. Because what is x01 of t? X01 of t is the magnitude of output signal whenever input signal is at positive magnitude, that is x1 of t. Then we consider the corresponding output level as positive magnitude output level as x01 of t. And what is x02 of t? X02 of t is the output magnitude, output signal magnitude whenever the input is at negative level. Whenever the input is at negative level. So the difference between the positive magnitude and negative magnitude levels is defined as the output signal, that is x0 of t. Here why capital T? Here why we represented capital T? Because at one particular instant of bit interval, we evaluated that. Okay, so x0 of t divided by sigma whole square. So that is nothing but the internal factor of P. That is the complementary error function. So rho max will be x0 of capital T divided by sigma whole square. So it is equal to, already we calculated this expression in the second module. How we got the square of output SNR rho max? We obtained this as integral minus infinite to plus infinite mod x of f square divided by Sni of f df. Okay, so here we'll assume that the input noise is white in nature, because we'll get the best response if you consider the matched filter. Okay, so that's why we'll assume the input noise power spectral distribution as white noise. Okay, the Gaussian noise is assumed to be white. So we consider optimum filter plus matched filter. What it means? Here the input Gaussian noise developed by the optimum filter is, it has that mean that with like around the mean we'll have the uniform distribution. Okay, so bell shape, like blunt bell shape response. Okay, so the white noise has uniform power spectral density. You know that one. The input noise power spectral density is equal to N0 by 2. What is Sni of f? Input noise power spectral distribution, which is the Fourier transform of the input noise. Input noise we assumed as N of t. In module 2, we assumed it as N of t. So the Fourier is N0 by 2. So now please substitute Sni of f in the square of output SNR expression. So rho max will be integral minus infinite to plus infinite. We have N0 by 2 in the denominator. We have N0 by 2 in the denominator. So take this to the numerator. So we will get as 2 by N0 integral minus infinite to plus infinite mod x of f square df. 2 by N0 integral minus infinite to plus infinite mod x of f square df. See, almost all we are following the same procedure as we did in the, because start from this point. We know that by using optimum filter we can derive the expression for probability of error. Then take this square and represent like this, and replace. Assume that the input Gaussian noise is white in nature. So white noise has uniform power spectral density. Replace as N0 by 2. So finally you will get square of output SNR as 2 by N0 integral minus infinite to plus infinite mod x of f square df. Even in examinations you should start from this point. Okay. Now next thing is using Parseval's theorem. I think you know what is Parseval's theorem. So it is square of integration of a magnitude of a particular function, particular signal in both frequency domain and time domain are equal. So in mathematical representation you can say that integral minus infinite to plus infinite mod x of f square df is equal to integral minus infinite to plus infinite mod x of t square dt. Okay, so we are applying the Parseval's theorem for a particular bit interval TB, which is also equal to t. Please represent here capital T. Capital T is equal to TB. Okay. So here we are representing during the bit interval capital T, which is equal to TB for the square of output SNR rho max. Then you will get rho max as 2 by N0 integral 0 to TB mod x of f square df. Okay, so take this as 2 by N0 integral 0 to TB mod x of t square dt. Okay, so this we replaced by using Parseval's theorem. See, we are almost all following the same procedure. Now, but what is x of t? X of t is a change in the input signal. X of t is the change in input signal, which is equal to x1 of t minus x2 of t. Okay, so what is x1 of t? x1 of t is the positive magnitude of the input. x1 of t is the positive magnitude of the input signal, and x2 of t is the negative. X2 of t is the negative magnitude of input signal. Here this is a negative magnitude. Okay, so here x2 of t is the negative magnitude of the input signal and x1 of t is the positive magnitude. So the difference between the positive magnitude level and input like negative magnitude level is the change in the output signal. So that is x of t. So just we replaced x of t as x1 of t minus x2 of t mod square dt. Up to this almost all the derivation is same. What we did in the case of matched filter, we don't know the values of the input signal there. Okay, the input signal levels we don't know for the matched filter. So then what we did, we substituted the energy of x1 of t as some even and energy of x2 of t square like x2 of t as E2, and we like what we replaced, we replaced it in the form of a minus b whole square, and we split that and considered x1 of t into x2 of t. That is the autocorrelation function energy. Okay, so and that as E12. Okay, like that we did, but in the case of binary, you know the general format of ASK signal. So please substitute the positive magnitude level x1 of t in this location minus x2 of t. Please substitute. So rho max is 2 by N0 integral 0 to TB x1 of t minus x2 of t mod like the magnitude of x1 of t minus x2 of t square dt. Okay, but what is the definition of binary ASK? Almost all the derivation is same for the first two slides for almost all the kinds of systems, but it will change from the input magnitude levels. So binary ASK signal is defined as, how can we define the transmitted signal x1 of t, BASK signal? Here the positive magnitude x1 of t is, we replaced AC as 2 root 2ps into cos omega ct for data 1, and negative magnitude x2 of t is 0 for data 0. Now please substitute the positive and negative magnitudes of binary ASK signal in the square of output SNR. In the square of output SNR. Please substitute. So what is the, where you need to substitute? In the square of output SNR, rho max. So please solve and tell me how much value you will get. Take x1 of t as root 2ps into cos omega ct, x2 of t as 0. I request all the students, please kindly solve this expression and tell me what will be the rho max square of output SNR. So go through, take your material notes and solve this on your own and tell me the answer. So take 2 minutes time and please solve the rho max, because already we solved all the Matching filter, everything we followed the same procedure. So just to take x1 of t as root 2ps cos omega ct and x2 of t as 0. Okay. Okay. Please solve this. Solve చేసి చెప్పండి అమ్మా ఒకసారి. Take x1 of t as root 2ps cos omega ct and x2 of t as 0. And please solve the value of square of output SNR. So substitute x1 of t as root 2ps cos omega ct and x2 of t as 0, and this will be root 2ps cos omega ct square. So can any one of you tell me the answer for that? What can be the value of square of output SNR? How many of you are doing? Please raise your hand. Please just raise your hand. How many of you are solving that what I said to you? Please raise your hand. So no one is solving. How many of you are solving for rho max, for binary ASK signal? Please raise your hand in the chat box. So no one is solving. Emma, ఎవరు సాల్వ్ చేయట్లేదా? Please respond to me.
చేస్తున్నాం మేము.
Just raise your hand.
ఆల్రెడీ రైస్ చేసాము కాబట్టి మీకు చూపించట్లేదు మేము అది.
Okay. Only one person. So what about others? How many are doing that? Can be able to know that this many students are doing. Please raise your hand. Only one student. What about others? I'm not asking the answer. I'm asking that how many students are in process of doing the corresponding work. C2 మా C2 ఉన్నారా?
ఎస్ మ్యామ్.
చేస్తున్నారా?
ఎస్ మ్యామ్, హ్యాండ్ రైజ్ చేయండి.
ఎప్పుడు? ఓకే
2 minutes.
ఓకే ఓకే అమ్మా, ఓకే థ్యాంక్ యూ. వాట్ అబౌట్ అదర్స్? ప్లీజ్ రైజ్ యువర్ హ్యాండ్. What about the other students? Okay, so you do, meanwhile I will explain. So because almost all you should follow the same procedure, that's why so once you know this procedure you can easily solve the probability of error for all the kinds of systems. So what next I told to you, take the rho max expression, and that is 2 by n naught integral 0 to t b x1 minus x1 of t minus x2 of t square dt. Okay, so if you square this, how much you will get? Root 2ps whole square, that will be 2ps into cos square omega ct. So 2 that will be 4ps divided by n naught integral 0 to tb. Here you have cos square omega ct dt. So minus 0, we left that part. Okay, so it is equal to 4ps by n naught integral 0 to tb. Just I replaced cos square omega ct as 1 plus cos 2 omega ct divided by 2 dt. Okay, just I replaced cos square omega ct as 1 plus cos 2 omega ct divided by 2. Okay, so then what we did? So these derivations you will get in the examinations. That's why I'm moving slow. So you should be capable of doing on your own. So just we replaced cos square omega ct as 1 plus cos 2 omega ct divided by 2. So then what we did, upon substituting the positive and negative magnitudes of binary ASK signal, the square of output SNR rho max is obtained as 2ps by n naught. Just I split into two integration parts. 1 plus cos 2 omega ct, I split into two integration terms. 2ps by n naught integral 0 to tb 1 dt plus 2ps by n naught integral 0 to tb cos 2 omega ct dt. Because divided by 2 you will have, so 4ps by 2 n naught will be 2ps by n naught. So here the integration of either the cosine signal or the sinusoidal component for the entire cycle is 0. Okay, so that's why second term will be 0. Second term integration will be 0. So you will get only 2ps by n naught into tb. Okay, how much you got? So finally you will get the square of output SNR rho max as 2ps by n naught into tb. Okay, then what we'll do? Please, now this is the square of output SNR rho max, but actually in the probability of error expression for optimum filter, you will get a relation between PE, that is probability of error, and amma చెప్పండి. Okay, C2 చెప్పండి అమ్మా. Okay, so kindly mute yourself. So finally you are interested only on output SNR instead of square of output SNR. So output SNR can be obtained by taking the square root of rho max. Okay, so then output SNR will be root rho max then you will get x01 of t minus x02 of t divided by sigma. So the root of this how 2 ps into tb divided by n naught. 2 into ps into tb divided by n naught. Now let us move to the next slide. So now please substitute the output SNR value, which is we obtained as root 2 ps into tb divided by n naught whole divided by 2 root 2 sigma, 2 root 2 sigma. So if you substitute here, you will have an extra value, that is 2 root 2. Please write down this expression. So here you have root 2 in the numerator and 2 root 2 in the denominator. ERFC of root 2 in the numerator and 2 root 2 in the denominator. So root 2 gets cancelled and you will have denominator, you will have 2 outside the root. So if you take this root inside, you will get 4 and not. So upon simplification, the probability of error for ASK system is obtained as PE is equal to half ERFC of root PS into TB divided by N naught whole divided by 2 whole divided by 2. So it is equal to half ERFC of root PS into TB divided by 4 N naught. So what is the probability of error expression for ASK system? Just upon replacing PS into TB as bit energy, you will get it as half ERFC of root EB by 4 N naught. Here bit energy EB will be equal to PS into TB. So now what is the probability of error expression for binary ASK system? It is equal to half ERFC of root EB by 4 N naught. If you observe the internal factor of complementary error function, it is EB by 4 N naught. That is, EB by N naught is reduced by how much factor? 1/4. But can any one of you tell me what is the probability of error expression for matched filter? Yesterday we discussed. What is the probability of error expression for matched filter? చెప్పండమ్మా, any one of the student, what is the probability of error expression for matched filter? H2 చెప్పండమ్మా అనుష్క. H7 ఉన్నారా? So what is the probability of error expression for matched filter? H7 is there. H7, please respond. అమ్మా చెప్పండి, అనుష్క ఉన్నారా? H2. Okay, H0.
Yes, ma'am. Half ERFC root over EB by N naught, ma'am.
Half ERFC of root over EB by
EB by
N
N
naught.
naught.
Okay, now you got the probability of error expression for binary ASK system as half ERFC of root EB by 4 N naught. So what you can conclude by comparing these two expressions?
Binary ASK అనేది 4 times decrease అవుతుంది, ma'am.
Yes. So if you compare the probability of error expressions, the SNR of our binary ASK system is reduced by 4 times. So that's why our probability of error will increase or
Actually గా
decrease?
2 times కదా, ma'am.
Oh,
2
okay.
times అనుకోండి, ma'am.
Okay, half. So if you take this outside, okay, you will get 2. Anyhow, what you can conclude from this statement? So the probability of error for binary ASK, is it high or low when compared to the matched filter?
Low, ma'am.
It is low.
Low.
Probability of error is low or high?
Yes, ma'am. Low, ma'am.
See here, the function is complementary error function. So complementary error function gives an inverse relationship between probability of error and the output SNR. So as and when the output SNR decreases, our probability of error will increase or decrease?
Increases, ma'am.
Increase. Okay, that's why in binary ASK system, we like mentioned the drawback of binary ASK as its probability of error is high because its SNR is low అని చెప్పి mention చేసాం. That is the reason that here SNR will reduce by a factor of 4. Okay, so inside the root, overall SNR will reduce by a factor of 4 because here we have SNR inside the root. Okay, so it will reduce. So once the SNR reduces, our probability of error will increase. So compared to the matched filter. So similarly, we can calculate the probability of error for binary PSK system and also for binary FSK, so that you can be able to compare the probability of errors for all these techniques. So here one of the comparison that you can say is that the probability of error for binary ASK system is more compared to the traditional matched filter. Okay, so now మా అచ్యుత్ మీరు ఒకసారి చెప్పండి, ప్రొసీజర్ చెప్పండి స్టార్టింగ్ నుంచి, హౌ వి స్టార్టెడ్ ద డెరివేషన్ ఆఫ్ probability of error expression for binary ASK system.
Yes, ma'am. Ma'am, first మనం probability of error expression తీసుకున్నాం, ma'am, for optimum filter కి, ma'am.
Okay ma.
Optimum filter expression half ERFC of x01 of t minus x02 of t by 2 root 2 sigma, ma'am.
Okay.
దాని తర్వాత మేము మనం స్క్వేర్ ఆఫ్ అవుట్పుట్ ఎస్ఎన్ఆర్ తీసుకున్నాం, మ్యామ్. రోమాక్స్ ఈక్వల్స్ టు ఎక్స్ ఆఫ్ టీ బై సిగ్మా, మ్యామ్. సిగ్మా హోల్ స్క్వేర్. దాని తర్వాత మ్యామ్ మనకి వైట్ నాయిస్ వల్ల పిహెచ్డి ఆఫ్ అదే పవర్ స్పెక్ట్రల్ డెన్సిటీ అనేది n0/2 అయింది, మ్యామ్.
ఓకే.
అది మనం రోమాక్స్ లో సబ్స్టిట్యూట్ చేసి మ్యామ్ పాస్కల్స్ థియరం ప్రకారం ఇంటిగ్రల్ మైనస్ ఇన్ఫినిటీ ఎక్స్ ఆఫ్ ఎఫ్ హోల్ స్క్వేర్ డిఎఫ్ ఈక్వల్స్ టు ఇంటిగ్రల్ మైనస్ ఇన్ఫినిటీ ఎక్స్ ఆఫ్ టీ హోల్ స్క్వేర్ డిటీ కింద రాసుకున్నాం మేము.
ఓకే.
రాసుకుని మేము మనకి ఎక్స్ ఆఫ్ టీ అంటే x1 ఆఫ్ టీ మైనస్ x2 ఆఫ్ టీ కదా మ్యామ్. x1 ఆఫ్ టీ అంటే పాజిటివ్ మ్యాగ్నిట్యూడ్ ఆఫ్ ఇన్పుట్, x2 ఆఫ్ టీ అంటే నెగిటివ్ మ్యాగ్నిట్యూడ్, మ్యామ్. మనకి నెగిటివ్ మ్యాగ్నిట్యూడ్ దగ్గర అవుట్పుట్ అనేది 0, మ్యామ్, ఫర్ బైనరీ ఏఎస్కే. పాజిటివ్ మ్యాగ్నిట్యూడ్ దగ్గర అవుట్పుట్ అనేది √2πs cos omega ct, మ్యామ్. అది సబ్స్టిట్యూట్ చేసాం మ్యామ్. దాన్ని డెరివేట్ చేసి అదే మ్యామ్ దాన్ని ఇంటిగ్రేషన్ చేసి వచ్చిన దాన్ని మనం అదే మ్యామ్ పవర్ ఈక్వేషన్ లో వేసి చేసాం మ్యామ్, ప్రాబబిలిటీ ఈక్వేషన్.
సో ఫైనల్ గా ఎంత వచ్చింది మనకి?
ఫైనల్ గా ప్రాబబిలిటీ ఆఫ్ ఎర్రర్ ఈక్వల్స్ టు half ERFC of √EB by 4n0, మ్యామ్.
√EB by 4n0. So from this we can conclude that the probability of error for binary ASK is higher compared to the matched filter, traditional matched filter. Okay ma, thank you. Now let us move to the binary PSK. So ma చెప్పండి
మ్యామ్. అక్కడ ఏఎస్కే లో మేము మనం ఇంటిగ్రల్ కాస్ట్ టర్మ్ అలా వదిలేసాం కదా మేము, ఎందుకు మేము?
ఎక్కడ కాస్ట్ టర్మ్ వదిలేదు. జనరల్ గా మనం ఇంటిగ్రేషన్ ఆఫ్ కొసైన్, ఇప్పుడు ఒక సైన్సోయిడల్ సిగ్నల్ తీసుకున్నా లేకపోతే కొసైన్ తీసుకున్నా ఒక పర్టికులర్ సైకిల్ లో అయితే ఎంత దాని వాల్యూ ఇంటిగ్రేషన్? జీరో అని చదువుకుంటారు కదా మీరు.
Yes,
ఇక్కడేనా
ma'am. అంటే ఇక్కడ మనం
చెప్పేది?
తీసుకునేది ఎనర్జీ కదా మ్యామ్.
ఎక్కడ బిట్
Actually గా
డ్యూరేషన్ లో మీరు ఇక్కడ ఇంటిగ్రేట్ చేశారనుకోండి హోల్ కాస్ ఏదర్ కాస్ ఒమేగా సిటీ ఆర్ సైన్ ఒమేగా సిటీ, ఇఫ్ యూ టేక్ ద ఇంటిగ్రేషన్ ఫర్ ద హోల్ సైకిల్. సో ఇక్కడ బిట్ డ్యూరేషన్ అంటే మనం బైనరీ ఏస్కేలో బిట్ ఈజ్ నథింగ్ బట్ సింబల్ కదా. సో సింబల్ కన్సిస్ట్
ma'am.
ఆఫ్ ఓన్లీ వన్ బిట్. అంటే
Yes,
వన్
ma'am.
పర్టికులర్ సైకిల్ మొత్తం తీసుకుంటే దాని ఇంటిగ్రేషన్ జీరో అవుతుంది.
ఓకే మ్యామ్.
ఓకేనా. సో అందుకని చెప్పి నెగ్లెక్ట్ చేశారు. అండ్ అనదర్ థింగ్ ఈజ్ మనం రిసీవర్ దగ్గర మనం ఈ సిగ్నల్ని ట్రాన్స్మిట్ చేసేటప్పుడు హయ్యర్ ఫ్రీక్వెన్సీస్ 2 ఒమేగా సి హయ్యర్ ఫ్రీక్వెన్సీ కదా. అంటే మనం జనరల్గా లో పాస్ ఫిల్టర్ టెక్నాలజీలో చెప్తే 2 ఒమేగా సి ఈజ్ ఎ హయ్యర్ ఫ్రీక్వెన్సీ. సో దట్స్ వై దిస్ హయ్యర్ ఫ్రీక్వెన్సీ కాంపోనెంట్ విల్ నాట్ బి అలౌడ్ అట్ ద రిసీవర్ సెక్షన్. సో మనం అవుట్పుట్ ఎస్ఎన్ఆర్ కదమ్మా క్యాలిక్యులేట్ చేస్తున్నాం. సో 2
Yes, ma'am.
ఒమేగా సిటీ కాంపోనెంట్ విల్ నాట్ బి అలౌడ్ బై ద లో పాస్ ఫిల్టర్ అని చెప్పేస్తాం యాక్చువల్గా అయితే. బికాస్ దే ఆర్ క్యాలిక్యులేటింగ్ ద అవుట్పుట్ ఎస్ఎన్ఆర్. యాక్చువల్గా ఇంటిగ్రేట్ చేస్తే యూ విల్ గెట్ ఇట్ యాజ్ జీరో. సో హయ్యర్ ఫ్రీక్వెన్సీ, సో దీస్ హయ్యర్ ఫ్రీక్వెన్సీ కాంపోనెంట్స్ విల్ నాట్ బి అలౌడ్ బై అవర్ లో పాస్ ఫిల్టర్. So that's why this integration will this factor will eliminate and will get only the output SNR as 2ps by n naught integral 0 to tb 1 dt. So ఈ ఫ్యాక్టర్ మాత్రమే మనం కన్సిడర్ చేసుకుంటాం. అండ్ ఈ ఫ్యాక్టర్ని నెగ్లెక్ట్ చేస్తారు ఎందుకంటే దిస్ ఇస్ హయ్యర్ ఫ్రీక్వెన్సీస్ అని చెప్పి అట్ ద అవుట్పుట్ లో పాస్ ఫిల్టర్, బికాస్ వీఆర్ క్యాలిక్యులేటింగ్ ద అవుట్పుట్ ఎస్ఎన్ఆర్. ఈజ్ ఇట్ ఓకే అచ్యుత్?
Yes, ma'am. Okay, ma'am.
So, okay, with this we can conclude our probability of error calculation for binary ASK system. And at the same time, you should remember the output SNR for binary ASK system. How much you got? Can చెప్పండి ఒకసారి అవుట్పుట్ ఎస్ఎన్ఆర్ ఎంత వచ్చింది మీకు? In the derivation, what is the value of output SNR? So if you go through
Half
this, you
year
can
FC into
అవుట్పుట్ ఎస్ఎన్ఆర్ మనకి రూట్ ఆఫ్ 2 EB by n naught వస్తుంది. సో అవుట్పుట్ ఎస్ఎన్ఆర్ ఈజ్ రూట్ 2 EB by n naught. ఓకే, ప్లీజ్ రిమెంబర్ దిస్ ఎక్స్ప్రెషన్. సో మీకు ఎగ్జామ్స్లో ఆన్లైన్ బిట్స్ అడిగేటప్పుడు యూ విల్ గెట్ దిస్ టైప్ ఆఫ్ క్వశ్చన్స్. ఓకే, సో అవుట్పుట్ ఎస్ఎన్ఆర్ ఫర్ బైనరీ ASK సిస్టమ్ ఈజ్ హౌ మచ్? రూట్ 2 EB by n naught. Okay, square of output SNR is 2 EB by n naught because 2 PS into TB divided by n naught is nothing but 2 EB by n naught. So can you compare this with the general baseband signal receiver? In the case of baseband signal receiver, we got the Romax, that is output SNR as 2 EB by n naught only. Okay, but here the probability of error is will increase because its SNR is reduced by a factor of like 4. Okay, so next in the same procedure you go through the calculation of probability of error for binary PSK. Okay, so follow the same procedure. I request all the students to follow the same procedure and solve for the probability of error for binary PSK. So here we can be able to derive the expression for probability of error for BPSK system. See, please follow the same procedure as I said to you up to the difference between the square input signal levels. Now I request any one of the student please tell me what are the two input signal levels for BPSK signal. What is the value of x1 of t and what is the value of x2 of t? Can any one of you tell me? So what is the general form of BPSK signal? D9, D9. D9, are you there? E0, G5, G5,
Yes, ma'am.
okay. Can you tell me the general expression for binary PSK signal?
Ma'am, don't know, ma'am.
You don't know? Okay, okay, thank you. See, go through the module, like, see, already I am uploading each and every topic in the WhatsApp, in your WhatsApp group. Please go through the material and please be thorough, with the derivation, like, at least with the expressions of the corresponding signals. G2, 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 G1, G1, G3, G4, G6, G7, imma G series anta absent పెట్టేయచ్చా except G5, G7, G9, G9, H2, Anushka, Narma, H2, H3, H4, H4, H6, H6, H8, H8, H9, H16, lateral entry 16, 17, 18, 18.
Yes, madam.
Narma. Okay, so after 20 students, only roll number 18 was present, I think. I think I can mark all of these students as absent today. So for starting from almost all G1 to, so our almost all 17, can I mark all of you as absent? Ma, can you please define the binary PSK signal, general form of PSK signal?
B of t into AC cos omega ct.
AC cos B of t
Omega.
into AC cos omega ct. Very good. Okay, very good. Okay, what is B of t?
Madam, +1 for x of t is equal to 1, -1 for x of t is equal to 0.
Okay, very good. So that's why you can say that it is AC cos omega ct for data bit 1 and minus AC cos omega ct for data bit 0. Okay, very good. So how can you replace the amplitude of carrier in terms of power dissipation per symbol, power dissipated per symbol?
Root 2ps into cos omega ct.
Okay. Okay, very good. Okay, now can you, okay, thank you. Now can we now follow the same procedure what we did for BP like BASK signal, follow the same procedure and take x1 of t as root 2ps cos like omega ct and take x2 of t as minus root 2ps cos omega ct. Okay, that is for data bit 0. So take x1 of t and x2 of t, substitute and get rho max and take root rho max for calculation of output SNR. Please substitute in the same expression to evaluate the probability of error. So take this as homework for you and try to complete it by the next class. Okay. Okay, any doubts?